Okay, I sure hope this works. I can't get into Canvas. I do not believe your lab for tonight is uploaded because the last time I was in Canvas, I was uploading the lab. And the upload hung halfway through, and I haven't been able to do anything with Canvas with the session that was logged in or logged in again anywhere. I also don't think you guys can get into Canvas, nor your email. I can't get into Napa email either. And the reason I think that is there are five students that have emailed me over the course of the semester. I wrote all of you and said, hey, is there a problem? Can you get into Canvas? But you all have napavalley.edu email addresses, and 0 people have gotten back to me. So, sorry for leaving everybody out in the ether. I couldn't even make an announcement that I was having technical difficulties and this lecture will be on YouTube because I can't get into Canvas to make announcements. I tried 2 different computers, 2 different browsers on each computer, and my phone. Nothing. So I'm guessing I'm being afflicted by the same thing that afflicted you when you were having Canvas difficulties. And maybe it's a campus-wide sort of thing. I don't know. But here we go. I'm sorry this isn't interactive. I'm sorry you can't ask questions. I'll be back someday. So as you go through this lecture, do so with a pad of paper and a loose sheet of paper so you can both take notes and write down any questions you have concerning this video, which you are hopefully going to watch on YouTube. I have planned to show a couple of YouTube videos and use a couple of applets, but YouTube is much, much, much pickier about allowing people to upload videos with any kind of content in them that they consider copyrighted. And they're also pretty strange about what's copyrighted and what's not. So this is going to be nothing but board work. So as long as my face and the concept of math is not copyrighted, you'll be able to hopefully watch it all on YouTube. Anyway, let's get right into it. Stuff that's left in this chapter. Bragg diffraction. So most crystals are basically layer of crystals, layer of crystals, layer of crystals, layer of crystals. We want to analyze the layers of crystals. You want to know, for example, how far apart they are from each other, the layers, that is. So let's see if we can figure it out. Layer of crystals, layer of crystals, and then we've got some incident probing beam that hits the second layer. Some portion of it will bounce back. Another incident probing beam that hits the first layer. Some portion of it will bounce back. Just as when I did thin films. This is all highly exaggerated. These things would not be coming in at anywhere near so extreme an angle as this. It would be coming in close to the normal. But I have to show them as being offset in order for there to be any kind of geometry associated with this. So the distance between the crystal planes, the thing that we are presumably interested in, is D. Let's go ahead and set up some algebra for you. It's coming in at an incident angle of theta. It's not coming in perfectly to the normal. So this is theta. This is 90 degrees. Oh, sorry. So this is theta. Nope, I'm still wrong. I need to do my geometry back. Right. This is theta. This is theta. This is also 90 degrees. This is D. So the path length for constructive interference is m times lambda equals D sine theta plus D sine theta. D sine theta, D sine theta. M lambda equals 2D sine theta. So you work out the path difference, you get some kind of mathematical expression that you can use to do something. So let's say that you're shooting some X-rays at the crystal. So the X-rays have a characteristic wavelength of 5 times 10 to the negative 10 meters. And the first order reflection is at 30 degrees. Sorry, I looked down at my notes as I was writing. So what is this space? What is the distance in between the two planes? What is D? And then the fancy word for this would be interstitial space. Pause if you still need to copy. We're using m equals 1. So let me just rewrite the whole equation so you don't have to hit rewind. And lambda equals 2d sine theta. So d is 1, 5 times 10 to the negative 10 meters. Divided by 2 times sine of 30, which is just 0.5. So D is 6 times 10 to the negative 9 meters. And that's how far the crystal planes are in between each other. So this doesn't sound like something that would have a whole lot of applicability to the world, but it does somewhat. There's normal crystals you can investigate, and everybody is interested in the crystalline structure of anything because we're scientists and we want to know everything about the world. You can also do things like take a substance like peanut butter and chemically remove a substance that is a known quantity, like a known crystal, maybe something that's harmful to you. And then you can use this technique and sweep light all across it. And knowing what D is, you can get a sense of how much of this harmful chemical there is. So there are some real useful tricks you can use with Bragg diffraction, but practically speaking, all the problems you're going to do are going to be finding the distance in between the plates. Or perhaps you'll be given distance and need to find the angle, such as to effectively determine where the first order effect is or the second order effect is, in which case m will be 2, so on and so forth. But I don't even think you have any problems with that, like that. I think it's all finding the first order effect. Okay. Particle wave duality in various contexts. Can a photon have momentum? Well, you already know from the very first chapter we did that a photon can exert force, so absolutely it's going to have a momentum. And a photon is going to be carrying energy as well. So the energy of a photon is h times f. That is something we've been knowing for a while. It's also h bar times omega. we're going to increasingly be using the unit omega as we jump into quantum mechanics. Remember, omega is just another slightly different version of f that sine and cosine functions will talk to a bit more effectively. If we want to determine what photon momentum is, we take that equation that I gave you last time, E squared equals P squared C squared plus M squared C to the fourth. Photons have no mass, so P is the square root of E squared over C squared is equal to E over C, plus or minus, but in this case I'm going to assume that the momentum is positive. And so P is equal to HF over C, and that's the same thing as H over lambda, which is how it is normally written. So this is the momentum carried by a single photon. And this requires the photon to be acting like a particle, which means it's going to be interacting with matter. It's not, all right. Which means it's going to be interacting with matter. It's going to be absorbed by something made out of matter. And that makes perfect sense because we would want something to be measured as having momentum when it's interacting with something else. We have talked about the photologic effect pretty exhaustively by this point. So now it's time to talk about different versions of the atomic models. So I'm going to start you out on the Plum Pudding model. And the idea behind the Plum Pudding model, or I would call it the chocolate chip model, is that there's a kind of a positive substrate that comprises what an atom is. And so this would be the dough in the chocolate. And then, buried within that dough, are various electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 positively charged things. I would need 11 negatively charged things to represent a nucleus that is not ionized. With ionized being when a certain number of the electrons have been knocked off. Okay, so this is a Plum Pudding model, and the Plum Pudding model came into serious doubt when you had a radioactive source that was shooting out alpha particles. We haven't talked about radioactive decay yet. That will be at the very end of the class. But alpha particles are basically a doubly ionized helium-4 nucleus, which means it's got 2 protons, 2 neutrons, no electrons when it is shot out as a form of radiation. So we knew that the negative charges were really small things, and we knew the positive charges were really big things, but they're all evenly mixed in through here. And there was an experiment done, I think, by a guy named Rutherford, but it doesn't really matter, and I don't want to comb through my notes to find out, but there's been at least 3 famous physicists named Rutherford, all members of the same family that were working at this time, and so odds are pretty good that it was a Rutherford. So you've got a bunch of alpha particles going this way, and the expectation is that because the electrons are kind of this plum pudding thing, if you take a gold sheet, the only things within it that would be able to really interact with this big old alpha particle would be the negative bits in it. Because there's equal amounts of positive and negative things, but the positive things would be this kind of substrate that's spread out everywhere, and so the alpha particle should pass right through them if they aren't repulsed by them, because positive things hate positive things. But the expectation is they won't be repulsed by them because there should be as many negative things in this gold sheet as positive things. So you get a range of results. And the most surprising results is that some of these alpha particles bounced right back. Now, this is completely not compatible with the plum pudding model, because the plum pudding model speculates that there's a bunch of tiny, small negative things and positive things are equally spread out everywhere. So the only thing really to bounce off of is the negative thing, and that would be attracting the alpha particle anyway. The thing that the alpha particle bouncing back implies is that there's something in the gold that is positive and hard and able to physically bounce back an alpha particle. So something in there is positive and massive. This is really pretty much the death of the plum pudding model, but a good new model hasn't come forward yet. Let me now talk about why we knew that electrons were small things. There's another guy named J.J. Thompson. He did a bunch of experiments with something called cathode ray tubes. And in order to get a cathode ray tube working, you basically take a piece of metal and heat it up so that electrons fly off. So you've got a bunch of electrons. We've got a bunch of electrons kind of flying off in every possible direction. But there's two capacitor plates right here, and they catch some of the electrons. There's a voltage difference, and so they accelerate them. So now we've got a beam of fast-moving electrons. And you have a new set of capacitor plates. That bend the electron beam. So now I'm going to apply a voltage to these capacitor plates. The electrons go doo -doo 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 -doo, and they strike probably a fluorescent piece of paper down here. So when it strikes with fluorescent paper, that makes the fluorescent paper glow, and you know where the thing hit. this was the classic E over M experiment. And while it wasn't able to independently generate what the exact numbers were for the electron to the mass, it was able to show that the electron to mass ratio of, the charge to mass ratio, E is a very poorly chosen letter there, it was able to show the charge per mass ratio for an electron is very small. And consequently, it being very small, it implies the mass of the electron is very small. So that was a known thing before the plum pudding model was developed. Probably part of the driving cause of the plum pudding model. I don't know a lot about it. Okay, I'm going to take a short break, which is the amazing thing about recording your lectures remotely. I'll be right back. Okay, where were we? J.J. Thompson's experiment. All right. Let's talk about what replaced it. And this is where quantum mechanics comes in. Once again, people made assumptions they did not really want to make. So, there is a gentleman by the name of Broglie. And he goes out there and he hypothesizes that maybe particles can be waves under certain conditions. I mean, it's just been shown that light can be a particle under certain conditions. I have an absolutely amazing YouTube video on this that I will be happy to share, but not right now because I want to be able to actually upload this. So de Broglie said maybe particles can be waves, and maybe their wavelength is their momentum, h divided by their momentum. At the time, there was no strong experimental evidence for this, but his thesis was taken and run with by some physicists, and they said, well, we've got a problem with the atom, so maybe we can fix it. What if there is positive core to the atom? I'm putting neutrons, but at the time nobody knew about neutrons. And the electrons are in orbit around it. This, by the way, is not the right model. I'm just showing it to you by way of an example. Now, there's an immediate problem with this, which is that anything that's going in a circular motion is accelerating. Accelerating particles radiate light. As a consequence of this, an electron in orbit around a strong, positive, heavy source would go like this, very quickly. It'd radiate off some photons. In no particular direction. I'm sorry that I'm drawing the photons as going away from the center of the atom. And as they radiate off photons, they're losing energy. And as they lose energy, their orbit would decay and they'd end up hitting this thing super fast. So nobody really believed this, as is so often true of so many of the theories that were put forward at this time. Once again, it was Niels Bohr who put this idea forward, sticking to Broglie's idea that maybe particles can be waves as well as acting as particles. He once again makes an assumption that he disliked and did not really believe. He said maybe, number one, electrons can orbit without radiating. And number two, the frequency of the electrons, the wavelength of the electrons, is somehow related to the size of the orbit. And also, it was by this point very well known that atoms can be made to release light if they're electrified. So you take a tube of hydrogen, which is easy to get. You just use electrolysis on water. You get half hydrogen, you get 2 times as much hydrogen as oxygen, and the hydrogen is much lighter. It takes up overall much less space, but whatever. You can get hydrogen. You electrify it. You shoot it through a prism. Of course, the hydrogen is shining out in all directions, but I'm going to constrain it to be a beam by means of using a single slit. Not so small that it's going to cause any diffraction effects, but small enough that it's just letting a single beam of light through. And then the prism splits the light into a strong red beam. Gosh, I've forgotten what the colors of hydrogen are. There's a really strong red one. That's why you see nebulas as being red, because that's the easiest way to get hydrogen to emit something in visible light. I think there's 2 turquoises close to each other and a weak purple. But don't quote me on that. My notes don't actually say, because I usually have this memorized, but it's been so long since I've done a spectroscopy lab that I don't actually know. It's not like I'm doing them in class with you guys. So assumption number 3 is that the light that comes from electrified atoms is somehow related to the transitions in between these different orbits. Yep. All the way down. So, as you can see, there's many problems with this. And as it happens, this entire model is wrong. It happens to give you the right answer, but it's one of those situations in physics where you get the right answer for the wrong reason. So let's go ahead and work through a wee bit of math to see the results, which are right answer for wrong reason. Again, I'm giving you almost no time to copy anything down from the board, so just use the pause button or the rewind button as necessary to capture all this information. Okay, so the angular momentum associated with the atom, m cross r. All right, I write crosses this way, but I'm going to try to, out of deference to American sensibilities, write it like that. So that's a cross product. I just like writing it that way because x is used for so many other things. It's equal to n times h over 2 pi. So n times h over 2 pi, it would be, in some sense, the angular momentum of these paths. Ooh, you use energy conservation, 1/2 mv squared, and Coulomb's law to represent the potential energy due to a system. And you can go ahead and solve for V as being the square root of K, capital Q, little q over mr. So that allows me to solve for r as being n squared, h bar squared, m squared over k, capital Q, little q. For n equals 1, the hydrogen atom, so Q would just be 1 in each case, you get a size of R, which in terms of the size of an atom is typically called A, with a naught down there. So A naught would be the lowest possible orbit, A1 would be the next highest orbit, A2 would be the next highest orbit. You could also call this R sub n. So this would be R sub 0, R sub 1 would be A1, R sub 2 would be A2, but whatever. The effective minimum radius of the electron orbit would be, plug in all your numbers, 0.529 angstroms, where an angstrom is 10 to the negative 10 meters. It's a unit that's only used to describe atomic size, as far as I know. Another way of writing this would be 0.0529 nanometers in more familiar units. Let me go up. It's a good thing that y'all can zoom backwards and forwards. Sorry, I didn't realize I was writing off the edge of the screen. So pause, copy, resume. So the energy released going from one orbit to another would be the energy of the photon, h times f, is equal to the energy of the higher orbit, the further out orbit, minus the energy of the more inward orbit. You do it the other way around, from outward to inward, you get negative energy. So I know what these quantities are from the previous board, and I'm going to get the mass of the electron, k squared, z squared, which is the atomic number, e to the fourth over 2 h bar squared, 1 over n squared minus 1 over m squared. Fortunately, let z equal 1 because hydrogen has an atomic number of 1, and you get knocked out once all those quantities are plugged in. 13.6 electron volts. 1 over n squared minus 1 over m squared. This is for hydrogen. And for hydrogen, the atomic number is equal to 1. So this equation works less and less and less well as you go up to higher and higher and higher atomic numbers. Like, it works pretty much perfectly for z equals 1, and it works less and less well for z equals other numbers. So z equals 2, it's a fairly good approximation. Z equals 92, which would be gold. It's an extremely bad approximation because it's not a true quantum mechanical result. I'm looking for a page that has information that I need. I don't see it, so I'm going to have to rely on my memory. And I'm pretty sure my memory will get me there. Okay. So let's consider hydrogen. This is the orbit closest to the nucleus. The orbitals get closer and closer together as you go higher. So this is n equals 1, n equals 2, n equals 3, n equals 4, and this one would be n equals 5. So when you're dropping down to n equals 1, I am 90% sure that this is called the Lyman series. And, oh, great. Hold on, I'll be right back. Hello, hello. Okay, that works. Great, video is back. And the Lyman series emits entirely ultraviolet light. Now, if the energy is dropping to n equals 2, my memory is kind of jogged a little bit. I'm going to say that this one is still a kind of a turquoise color, but maybe more of a greenish one. That this one is more of a purplish color. This is definitely called the Balmer series. And it's the only atomic transition for hydrogen that generates visible light. So this is why you get a pink glow from electrified hydrogen. This is why whenever you see a neon sign that's pink, it's hydrogen. It's not electrified neon, it's electrified hydrogen. Electrified neon is extremely red. And the final transitions, well, not the final transitions, but the most common transitions that are available to hydrogen is called the Passion series. And this emits entirely infrared light. And that can be confirmed because by this point we had techniques to detect infrared light. You use a prism and you put a bunch of thermometers all around the prism, and infrared light will heat up the thermometers even if the light that makes it up can't be seen by human eyes. So alignment, Passion series, 100% for sure right. Balmer series, well, it's predicted by this math, which is 13.6 electron volts, 1 over m squared minus 1 over n squared. That works perfectly for this. That works perfectly for this. This is at this point highly theoretical, but it seems like what Bohr predicted with this math that he didn't believe himself described the atomic model perfectly. So after this point, we have the Bohr model. Well, I guess I didn't know about neutrons yet. So let's just use a hydrogen atom, which normally doesn't have a neutron. If it does, you call it deuterium. If it has 2 neutrons, you call it tritium. So this is the new model of how atoms work. And that's taken us right up to the end of the chapter. And so I'm going to hit stop recording and put this up on YouTube. Hope everybody's been having a great day. I'm going to look for some responses for the students I emailed, and I'll see if your Napa Valley email works. Bye.